Okay. All right, so we can get closer to experiment, but we're still missing a couple of effects. In gallium arsenide, aluminum arsenide, for example, you might think of a single barrier structure like this. That's an effective mass point of view of a single band at gamma. It turns out that aluminum arsenide looks very much like silicon. The lowest band edge is actually at X, close to X. So it's actually an indirect gap material. What does that mean in a heterostructure like this? Well, the X point in gallium arsenide is actually higher than the gamma point, and in aluminum arsenide it's much lower than the gamma point. And it's so much lower that actually it looks like a quantum well in the X bands. Right? The dashed line looks like a quantum well versus the solid line looks like a barrier. Well, what does a quantum well have? Bound states. Okay? There's going to be states in this barrier. Resonance states. What can you do with resonance states? You couple to them, you transmit through them. They're like an open gate to go through. All right? Does that matter? Yeah, so here is a density of states plot of a gallium arsenide, aluminum arsenide structure, and an aluminum arsenide barrier in gamma looks huge. It's like 1 eV tall. But the fact is, the effective barrier is only roughly 200 millectron volt tall. Because the X point actually dips down and becomes a well, and your central resonance is now starting to talk to these complicated resonances in the X points. It resonantly couples to those. So what you thought was a nice big barrier turns out to be a nicely resonantly enhanced current flow that you can get through the structure. And the result is, in a device like this, where you have these multi-band effects in aluminum arsenide, you can actually overlap experiment nicely if you have a full band approach. In a one band approach, your current is completely off. That's the third physical effect of multiband. Now there's a fourth one that is actually related to the first one. It has to do with band non-parabolicity. But I'm going to walk you through that a little bit slower, hopefully. So normally, when you do carrier transport, you have to integrate over the degrees of freedom that the electrons have. So what degrees of freedom do these electrons have? Well, they have an energy, and in a 1D device, they have transverse degree of freedom, right? They can flow at an angle in X and Y. So they can have transverse momentum. Not everybody needs to go straight through the structure. They can go also through an angle. You may be able to, in the conduction band, approximate that with saying, I'm going with a momentum and an angle. And what you typically do is you integrate out the angle and say, I'm just going to make it energy and momentum dependent. And in fact, what most people do is they forget about the momentum dependence and integrate out analytically the K dependence, assuming that the bands are parabolic. So this bottom formula is what typically is being used in the field for resonant tunneling diodes for current integrations. What I'm going to show you is that at minimum you have to do the second equation from the bottom that includes the transverse K integration. And I'm going to argue why that is. So for a material system that is reasonably parabolic, you can compute the following things. So on the top left, you see a transmission coefficient through the structure that we looked at. And you look at the transverse momentum dependence of these resonances. So this is sort of in the transverse plane, transverse to the carrier transport, there's a dispersion. And these things look roughly parabolic in gallium arsenide. So as you align this resonance here with k equal to 0, and you shift up your k, this transmission just goes up like this. And in fact, this transmission coefficient here on the right looks roughly the same as the transmission coefficient on the left. It's just shifted up in energy on a nice parabola. If it's a perfect parabola, they're perfect shifts of each other. And if they're perfect shifts of each other, you can actually integrate that out analytically. So in gallium arsenide, that actually roughly works. Again, here's a sketch on what is meant by this transverse momentum. You don't have to just go through straight, you can go through at an angle, and then you have a degree of freedom here that is the transverse momentum. So now let's look at these running integrals that I have shown in the previous lectures, where we say, okay, we have a transmission coefficient multiplied by a Fermi function, that's our current density. We can integrate that and sort of get a step function, so we know where an energy current is flowing. And if we do this for multiple k's, where this transmission or the current density moves up in k, we sort of get multiple step functions like that. And these are not normalized. In the previous lectures, I always had normalized them to 1. So now you can sort of see how this value here is decreasing with k. Right? The current flowing in the transverse direction with k is decreasing. So you could plot that. So here is the transverse momentum, and here is sort of the peak value of these the integral as a function of k. So it's decaying nicely. So that looks all nice when you have a parabolic-like material. So I'm going to resurrect this graph right here. You see how the transmission is aligned with these dispersion. And here is a J of k diagram plotted like this. So as a function of, as you crank up k, your current decreases and eventually it drops sharply. You can plot this also in voltage space. So here's now voltage and momentum. And what you kind of see here is a dispersion, right? Here's a k dispersion that gives you a cutoff, and you also see sort of almost a sea of electrons that you can provide supplies in voltage. Right? You pull this resonance from below into a sea of electrons that's pretty narrow, and it gets bigger and bigger, and at some point, at a higher voltage, the sea of electrons vanishes and the current decreases and there's no current. Eventually you get to a higher state and there's a sea of electrons. It's sitting in a parabolic puddle. And if it's really parabolic, it doesn't matter whether you do an analytical calculation or not. Okay? That's the show and tell of this part. But indium gallium arsenide is very non-parabolic. And if you just did a calculation without a full band integration, without a transverse integration, you calculate a curve that is comparing to experiment in blue and green. You calculate a curve in red here that is overshooting the peak, and it is not getting the valley current right. On a log scale, you can see that again. It's overshooting the peak and it's not getting the valley current right. And a 2-band model or a 1-band model don't get even close. So, going back to this, at the minimum you have to do this double integral of k integration, and here's the reason why. So you have here's a bias condition of an RTD where you have a central resonance. It's talking to a resonance in the emitter, and they're strongly coupled, and they form a bonding and anti-bonding state. So you can barely tell them apart. Okay? They just form the bonding and anti. So this is in perfect resonance between these two states.